Hello, everyone. My name is Inon. Thanks for being here at this time of day. I'm a senior data scientist in Pendo. I have about 10 years total experience in machine learning, both in academia and in the industry. And in this talk, I will talk about data science in real life, concluding with don't underestimate the obvious. So, when we talk about data science, as many of you probably know, we are talking about a job or a role where you need to take data and extract useful insights from it. The end goal usually is to build some model of the realistic phenomenon, such that the model is an approximation that can be used to gain those insights. And data science itself, the science part is based on many mathematically grounded tools, algorithms, and other methods, where in industry, the goal is to use all those to grow from lots of data to some usable product. Well, that's the pitch, but in actuality, in real life, data science meets Murphy's Law a lot of times. If anything can go wrong, it will go wrong in data science. And this includes all sorts of mistakes that we do, the data scientists, assumptions that we make at the beginning of the modeling process that turn out to be wrong later on. It includes stuff like models that look so good in the lab, but underperform out of it. And sometimes we go a long stretch only to realize that the market needs for the product that we are building are different than the models that we built. So in this presentation, I'm going, as I said, to talk about real life data science with a bit of Python examples. And I will tell it through 3 points, one being actual failure stories, the other being kind of a list of common pitfalls that you encounter. And I'll then continue to how to mitigate those problems. The target audience for this talk is people who are neophytes to data science, so beginner plus also in Python, but I think that there is a bit of everything for everyone also. So starting with an overview of data science, and to keep it really simple and really simplistic, when building a model of reality in data science, you are faced with a bunch of data samples that have been observed through some phenomenon. And these samples are usually given as numerical values, sometimes in tabular form. Then you face the task of modeling this by choosing some family of functions that can hopefully explain the correlation between X variables and the thing that you want to predict, let's say, which is the Y variable. And this function is actually your model, but it is a family of functions, so you also need to train it such that you get a specific family, a function from that family. And then the usual process is train your model or your function, check that it works well on unseen data or out of sample test data, and deploy your model, hold your fingers, and hope that it will work well in the real world. And when I wrote this presentation, I tried to classify for myself where are the main points of failure when it comes to real-life data science. And I kind of bucketed it into 3 categories, one being the data itself that you model, the other being the human factor, which is all the humans involved, particularly the data scientists, but also other people. And the third one is the external world, the outside world that you don't really have full control of. So I'm going to go over these 3 points, and for each of them tell you stories, a list of general pitfalls and mitigation tools, starting with the data itself. These are a couple of actual stories that myself and other team members faced. One of them worked on data of weather to predict weather in some environment, and they did a pretty good job, but they used only summer data. So when they deployed it in the autumn, it didn't work so well. Now, I'm sure that there are data scientists in the audience that say, well, yeah, but these are real life stories. This stuff happened. And the second one is that another one of my team members worked on a big project to extract text from websites. And they collected a good bunch of HTMLs from the web. But they didn't notice that a good portion of those HTMLs were just parked pages where you go into it and it says this domain is ready to be sold. And the text there is very different than what they actually aimed for. So the data backstabs usually in data science. And the general pitfalls, and this is by no means an extensive list because I can only fit so much in 20 minutes or so, but these are the general pitfalls that I thought of when it comes to data. And the maxim is, if you put garbage into your model, it doesn't matter how good it is, you'll get garbage out of your model. And when it comes to data, every data scientist encounters bad values in the data. Even if some good IT person extracted it from a database, there is always going to be stuff to clean there. And that includes the familiar missing values or NANs, not a number, formats that one sneaky value somewhere changes everything. It looks like a number, but then you realize it's a string. And sometimes it even includes different units within the same column, as in meters per second, kilometer per hour. So that stuff always goes wrong. Another kind of data hazard that you realize when you work with data is that sometimes, even if you work with big data, it is still insufficient because the real phenomenon exists in a pretty high dimension, and however many samples you got, it's still not enough to cover everything. In particular, as I said in the previous example, sometimes you need multiple years to model something that has seasonality and you don't always have access to it. And generally, as you know from previous lectures in Python, when you work with big data, it's going to take heavy resources at some point, much more than your own laptop can handle. So concerning these points in general, I try to narrow down to several rules of thumb on what to do to mitigate data pitfalls. And one of them is, of course, always check, always be suspicious that something lurks within. And you can also use synthetic data to your advantage, data that you generate and encompasses a lot of your assumptions so that you know that your system works well with it. And then if the system fails on real data, you can compare and check what was different. And in general, you might prefer to work with data where the stuff is already typed as types, as in units, etc. But we all work with CSVs. It will keep happening. So, I don't know, try to push that. And that's the first point. The other point is that when you work locally with big data, you can mitigate it to some extent by either taking a subsample of it. A random subsample is not so bad always if it still captures the distribution that you're trying to model. And as people before me talked about, you also have ways to use your hard disk or secondary memory using libraries that abstract the whole memory handling thing, such as DES. And eventually, in every big enough project, you need to be ready to scale. There will be a point where when you gather a lot of data, or work with a lot of data, you either try to mitigate that locally by parallelizing, or you go to PySpark and other distributed computing frameworks. And then you face the issues there, but at least you can process that much data. That was about data. The second thing where pitfalls lurk is us humans. And a couple of failure stories about that. One is I know someone whose PhD was about prediction of environmental conditions of sun exposure, etc. And he got a really great model, except that he contaminated the train set of that model with test samples, so it didn't work in real life. And then he had to scrape it and change direction in his PhD, but it worked out eventually. And in our own team, in Pendo, we at one day got just different results on different computers, and we didn't know why, because we all use virtual environments that install the same stuff until we realized that we made the old mistake of forgetting to specify package versions in our Python. And so one of us worked with a bit of a different code in the background, which yielded different results. So when talking about pitfalls in general, when it comes to us human, I would say that it falls either into data scientists making methodological mistakes in data science, or just plain human mistakes. And in methodological errors, I mean stuff like rush to a complicated model because it seems so awesome. But over-engineering a model can result in something that you cannot use well. As some of us know, I guess, you can overtrain a model or overfit it. You can underfit a model if you don't train it with enough data. You can do sneaky stuff like trying to train the hyperparameters of the model and thereby overfitting it also. And we sometimes, when we rush to do stuff, we mix apples with oranges, such as discrete and continuous distributions, and all sorts of numbers that look innocent but are from different worlds. Again, this is not an extensive list, but these are like the big issues. And human mistakes, as in any project, exist also in data science. When it comes to bugs, they always happen. And when you make assumptions about your data or the phenomenon you're modeling, some of that assumptions will turn out sometimes to be wrong. So a few points for mitigating those pretty common pitfalls. When you do modeling, prefer to start simple if you can, because then you get a simple baseline model that you can better explain and better reason about, and then use that to build more complex models and compare them back to how much improvement you have. And sometimes, in some cases, even the simplest models are the best. For example, when you work on time series data, that is data that is on the timeline, sometimes plain statistics are just really, really good. Another mitigation that I think I talked about also in data is you have at your disposal all kinds of testing tools in Python, including the famous Pytest for long-term correctness of your code. You can also resort to defensive programming, which is inserting all those small sanity checks in your code, just that if something really gross happens, then it at least explodes there. You may have seen that Python has already for several years type hints and linters that you can use to kind of guard yourself through types in the language. And eventually, in data science and I guess elsewhere, it's a team effort, and it's an environment that you work in. You're not alone. Use your teams to do the code reviews and try to make some team discipline so that different people don't generate two different code that doesn't work with one another. And there are resources out there to learn from others' mistakes and experience, such as towardsdatascience.com and many other blogs that I recommend to take a look at sometimes. Finally, within the realm of what can go wrong in data science, there is the outside world, and a couple of failure stories about that. There was a case where someone worked on a model. It actually was good. He didn't make a lot of mistakes. He fitted it well. It showed that it works well. But in the front end, the guys that made the visualization of showing how accurate it is made some mistakes, and it looked horrible. But it was good, actually. So the data scientist also depends on other members of the organization to show that the model works. And in a more extreme example, I know a company that made a really awesome model of how people interact with one another in all sorts of transactional data. It was really good, and they tried to push it to the market for 2 years until they realized that that's not what the market needs, and they pivoted completely from that model to something else. So you, as a data scientist, live in an actual world that consumes your results. And so generalizing it to all sorts of common pitfalls when it comes to the outside world, you work with APIs and libraries, and they will change. And sometimes those changes are not backwards compatible. So, and sometimes API change under your feet in a non-backward compatible way. That will happen, and you should prepare for it. When you deploy a model, you create a model that has been trained on past data, maybe very good, but in reality, some shifts in the underlying distribution of the data keep happening, and you should prepare for that. In particular, there are cases where your model does a good prediction job. So the people who consume those predictions operate on them, and then they change something in the environment, and there becomes a feedback loop where your prediction caused a change in the world that then you need to adapt to. And as I said, when you develop models in the industry, be aligned with the business needs and make sure that your models actually meet what actual customers need. Don't try to make an awesome model if it doesn't fulfill the business requirements. Several ways to mitigate those problems. One is proof of concept, as in start early with possibly design partners, and then use these few months to gauge your assumptions, to build stuff, to see that the customer actually needs that stuff, and that you can proceed from there to a full-fledged product. Of course, you should monitor your model in real life because stuff will keep changing. And when you develop, keep the end users in mind. Even though you're a data scientist or an engineer and you're focused on your work, there is a bigger picture involved. And unsurprisingly, all sorts of tests to alert when stuff changes are also very useful. So this brings us to the end of this presentation. And to summarize, don't underestimate the obvious. If it can go wrong, it will. You should expect 3 areas where failures can occur. One being the data itself that tends to backstab. Always check it and be ready to scale and test. The other is methodological errors and human errors, where you'd better start simple if you can and use others' experience to your advantage and more testing. And when it comes to the outside world, make sure that you start simple, advance progressively, monitor deployed stuff, and keep users in mind, and keep testing. That's it for this succinct presentation. Any questions?
Yeah, can you give an example of testing in production of your predicted model?
You mean test it, keep running in production?
Yeah, during to check the effect of the outside world.
Yeah, I don't have a very specific example for that or Python code. But let's say in models that try to do binary classification, as in answer a binary question, you have some measures of performance, as in how precise you are, how many of actual things that you wanted to label as this is true, this is false, you got right. So you keep monitoring that, and you at some point you notice a shift, as in, okay, something in the outside world changed. The proportions are not exactly as before. Maybe the performance is a bit low, and you need to investigate and try to improve. Yeah.
You mentioned Dust somewhere in the middle there.
Yeah.
The application, if I understood correctly, was just to load the CSV using Dust, or actually you were recommending using it in parallelize things?
Well, recommending is a bit of a strong word because I have a mixed experience with Dask. But basically, if you run into a situation where your main memory is not enough and you still want to try to do stuff locally, then you could give Dask a quick go because its API is very similar to Pandas, which is the library that data scientists usually use locally to do those data manipulations. So, and then you may find out that its abstraction, where it works with the hard disk and does all the heavy lifting for you, solves that bottleneck. The API is not always complete, so you cannot always do everything that you could do in Pandas, but it's very quick to shift to it and try. So.
Okay. Did you try one of the things that work on top of it, Refect or Coils or one of those?
Personally, no. I have experience in PySpark and Pandas, but.
Okay, so just a small comment. Prefect still uses Dask as an engine, but it also allows you a level of manipulating the tasks you're creating. So you can this actually follows your talk very well about things that can go wrong. So Reflect actually has this concept of negative engineering that you can do things, if they go wrong, you can actually tell them not to go wrong.
Okay, so the lesson is there is prefect, and it's another way to mitigate that stuff. But as you say, like it shows you more, gives you more observability into what goes wrong inside.
Yeah, so it's kind of a talk, but yeah, it's a discussion we can make later.
Right, thank you. Yeah.
It's not an answer about how you can monitor your model in production. There are tools like Supervise or Euphoria that you can use them when you're sending your data. You can attach what was the data you're getting and what was the prediction your model gave, and then it can show that the data that your model is using on the test set is different from you really getting on the production.
Okay.
So then there are tools that.
Nice to know. So Euphoria for like sort of continuous integration on field with the data.
I mean the name of the company is Supervise is one of them, and there are many more. But just this was a question example tool.
All right. Thanks for this other advice. Any other questions? All right. Thank you.